On September 14, 2025, an interstellar object designated 3I Atlas crossed the 29 million kilometer threshold, the point where solar radiation begins measurably altering volatile chemistry. The clock had already started ticking. This window is closing. Within weeks, outgassing will erase pristine interstellar signatures. Budget delays, telescope scheduling conflicts, and orbital geometry mean this may be the last clean look before the data is forever altered. What we observe now may never be observable again. Early spectra show carbon chain depletion, paired with unexpected neon green ion emissions, a chemical combination that should not survive interstellar transit intact.
Look at the spike.
The ratios are wrong.
Running
The alignment
now.
is wrong. Something about this
Waveform
object
stable,
refuses
but
to
the
fit the
amplitude
models
is
we've built
increasing.
from decades of comet science. Astronomers disagree. Some say contamination. Others say physics we haven't modeled yet. A smaller group won't rule out artificial surface processing, not because they believe it is, but because the math refuses to close. The data sits there, quiet and insistent, waiting for an explanation that hasn't arrived. Before we go deeper, hit like, subscribe, and tell me where you're listening from, because this story is still unfolding. The telescopes are still watching. The debate is still open. This is 3I Atlas. This is not science fiction. This is September 2025 title. Chapter 1, September 3rd. The object that should not have slowed. The first trajectory solution came back wrong. Not catastrophically wrong. Not obviously wrong. Just off. The kind of discrepancy that makes an orbit analyst pause, run the calculation again, check the reference frame, and then quietly send the file to a colleague with a single-line email. Am I seeing this right? On September 3rd, 2025, Dr. Elena Vasquez sat in the low-light control room of the Atlas facility in Hawaii, staring at a deceleration curve that shouldn't exist. The object now designated 3I Atlas, the third confirmed interstellar visitor to our solar system, was slowing down. Not dramatically. Not enough to suggest a gravitational capture. But measurably, consistently, and without explanation. Standard cometary outgassing could account for non-gravitational acceleration. We've seen it 1,000 times. A comet heats up, volatiles sublimate, jets of gas and dust erupt asymmetrically, and the object gets a tiny push, usually away from the sun. It's predictable. It's physics we've understood since the 1950s. But 3I Atlas wasn't accelerating. It was decelerating. And there was no dust plume. Vasquez ran the numbers 3 times. The deceleration was on the order of 0.03 millimeters per second squared. Small enough to be noise, except it wasn't noise. It was coherent. It was directional. And it had been consistent across 5 days of observation. The object had crossed into the inner solar system at roughly 31 kilometers per second relative to the sun, following a hyperbolic trajectory that screamed interstellar origin. But now, as it approached perihelion, it was bleeding velocity in a way that gravitational models alone could not explain. She sent the data to Dr. Mikhail Sokolov at the Jet Propulsion Laboratory. His reply came 18 minutes later. A symmetric jet? It was the obvious hypothesis. If 3I Atlas was outgassing unevenly, jets firing preferentially in one direction, it could generate a braking force. Comet 67P Churyumov-Gerasimenko had done something similar, but 67P had also produced visible dust. It had shown clear spectral signatures of water vapor, carbon dioxide, and silicate grains. 3I Atlas showed none of that. No coma. No tail. No detectable particulate emission. Vasquez pulled up the optical data from the Gemini North Telescope. The object was faint, magnitude 22.3, but it was there, a slow-moving point of light against the stellar background. She toggled to the infrared composite from NeoEyes. Still nothing. No thermal excess. No dust scattering. The object was reflecting sunlight like a cold, inert rock, not sublimating like an active comet. She called Sokolov. If it's outgassing, she said, where's the gas? Maybe it's just low density, Sokolov replied. Below detection threshold. Then how is it producing enough thrust to slow the object down? Silence on the line. Not the silence of someone without an answer. The silence of someone who has the same question and doesn't like it. By September 4th, the deceleration had been independently confirmed by the European Space Agency's Near-Earth Object Coordination Center. Dr. Carla Mendez, in Madrid, ran the orbital refinement using data from 3 different observatories. Same results. Non-gravitational deceleration, magnitude consistent with Vasquez's numbers, no corresponding photometric or spectroscopic evidence of cometary activity. Mendez published a preliminary circular to the Minor Planets Center. She kept the language neutral. Non-gravitational effects detected, origin under investigation. But in the internal ASA chat, she was more direct. This doesn't add up. Either we're missing something obvious, or the object is not behaving like anything we've cataloged before. The debate started immediately. Dr. Ramon Sikora, at the University of Arizona, proposed a spin-driven model. If 3I Atlas had an irregular shape and was rotating rapidly, differential solar heating could create small but persistent thrust without visible outgassing. It was plausible. It had been invoked before to explain the acceleration of Oumuamua, the first confirmed interstellar object, back in 2017. But Oumuamua had accelerated away from the Sun. 3 Atlas was decelerating toward it. Maybe the spin axis is oriented retrograde, Sikora suggested during a hastily convened Zoom meeting on September 5th. If the heated side is facing forward relative to the velocity vector, the thrust could act as a brake. Vasquez wasn't convinced. That would require a very specific geometry. And it still doesn't explain why we're not seeing any gas. Maybe the gas is transparent, someone else offered. Molecular hydrogen, helium, something that doesn't emit in the optical or UV. Then we should see it in the radio, Mendez countered. VLA should pick up molecular emission if there's any significant mass loss. The Very Large Array had been tasked to observe 3I Atlas, starting September 6. Until then, all they had were optical astrometry, low-resolution spectra, and a growing sense that something about this object didn't fit the taxonomy. Vasquez stayed late that night, alone in the control room, watching the data stream in from Atlas. The object was still there, still moving, still slowing. She thought about Oumuamua. That object had sparked years of debate, countless papers, and at least one very public argument about whether it could be artificial. The scientific consensus had settled on a natural explanation, probably a nitrogen iceberg, possibly a hydrogen iceberg, maybe a dust bunny held together by organic polymers. Exotic, but natural. But the discourse had left scars. The topic of interstellar objects now carried a strange weight in the community. Mention the possibility of something artificial, even hypothetically, and you risked being labeled a crank. So people didn't mention it. They danced around it. They used phrases like anomalous behavior and non-standard outgassing and unexpected thrust vector, and everyone understood what was not being said. Vasquez looked at the deceleration curve again. She ran a quick simulation. If the braking continued at the current rate, how much delta V would the object lose by perihelion? The answer was approximately 140 meters per second. Not enough to capture it into a bound orbit. Not even close. But enough to notice. Enough to matter. She drafted an email to Sokolov. Then deleted it. Then drafted it again. Mikhail, hypothetically, if an object wanted to slow down in the inner solar system without producing visible exhaust, what would it need to do? She stared at the sentence for 2 minutes. Then deleted it again. Because that wasn't the question. The question was, what could make an interstellar object decelerate without showing us why? And the uncomfortable truth was that she didn't have an answer. None of them did. Not yet. By the morning of September 6th, the data had propagated through the community. Emails were circulating. Private messages were being exchanged. No one was saying anything publicly, but everyone was thinking the same thing. This was not a normal comet. And if it wasn't a comet, what was it? Dr. Aisha Malik at the UK's Isaac Newton Group sent a note to Mendez. I've run the outgassing models with every plausible volatile composition. Even with pure I can't get the thrust-to-mass ratio to work without a detectable coma. Either this thing is made of something we haven't considered, or the deceleration isn't coming from outgassing. Mendes replied. Then, where is it coming from? No response. Because that was the question now. Not is this object outgassing, but what else could it be? The obvious alternative was solar radiation pressure. Photons carry momentum. If 3I Atlas had an unusually high surface area to mass ratio, like a solar sail or a fractal dust aggregate, the pressure of sunlight alone could create measurable thrust. But solar radiation pressure accelerates objects away from the sun. It doesn't slow them down. Unless the object was oriented such that reflected light was producing a net retrograde force. It was theoretically possible. But it required a very specific geometry. A concave surface, perhaps. Or a reflective face, angled precisely to redirect momentum in the opposite direction of travel. The probability of that happening naturally was low. Not impossible, but low. Vasquez printed out the trajectory data and taped it to the wall above her desk. She wanted to see it. Not just on a screen, but physically. She wanted to stare at it until it made sense. It didn't make sense yet. On September 7th, Dr. Hannah Orr at Caltech published a preprint on arc-CVTI. The title was deliberately neutral. Non-gravitational deceleration of interstellar object 3A Atlas. Observational constraints and preliminary models. The abstract was careful. The conclusion was cautious. But buried in Table 3, under alternative hypotheses, there was a single line. Directed thrust mechanism. Probability 1% cannot be excluded by current data. It was the first time anyone had written it down publicly. The object that should not have slowed was still slowing. And no one knew why. This is not science fiction. This is September 2025 Tetor. Chapter 2, September 6th. The telescopes we almost didn't get. The request hit the European Southern Observatory's scheduling committee at the worst possible time. It was September 6, 2025, and the Very Large Telescope in Chile was booked solid for the next 4 weeks. Sphere, the high-contrast imaging instrument designed to study exoplanets, was in the middle of a multi-night campaign targeting a young planetary system 300 light-years away. MUSE, the integral field spectrograph, had been allocated to a high-priority program studying galaxy formation in the early universe. X-Shooter, one of the most versatile spectrographs in the world, was scheduled for routine calibration and maintenance. And then Dr. Carla Mendez in Madrid sent an urgent email with the subject line: Emergency target of opportunity. Interstellar object 3 Atlas. The request was for 12 hours of observing time across multiple instruments. X-Shooter for high-resolution spectroscopy, Sphere for resolved imaging, and Force 2 for rapid photometry. The scientific justification was compelling but vague. Anomalous, non-gravitational effects. Possible outgassing. Time-sensitive opportunity. The object was brightening as it approached perihelion, but it would only remain observable for a limited window before solar conjunction rendered it inaccessible for months. Dr. Lucas Hartmann, chair of the VLT Observing Programs Committee, read the request twice. Then he checked the current schedule. Then he sighed. This is going to be a problem, he muttered. It wasn't that the science wasn't good. It was. Interstellar objects were rare. Only 2 had been conclusively identified before 3I Atlas, Ane Oumuamua in 2017 and 2I Borisov in 2019. Both had generated enormous scientific interest and dozens of papers. A third interstellar object, especially one exhibiting anomalous behavior, was absolutely worth observing. But the VLT wasn't just a research tool. It was a political instrument, a resource fought over by hundreds of astronomers, governed by Byzantine allocation rules, and perpetually oversubscribed by a factor of 5 to 1. Shifting an observation wasn't a simple matter of moving a slider on a calendar. It meant displacing someone else's approved program. It meant negotiating with principal investigators who had been waiting months for their telescope time. It meant justifying why this particular target was more important than everything else already on the schedule. Hartman called a meeting. By the afternoon of September 7th, he had assembled a small crisis group, representatives from ESO's Science Operations, the VELT Program Office, and the Outreach Team, which had been receiving increasingly pointed emails from journalists asking when the telescope would observe the new interstellar object. Everyone knew the optics were bad. If 3I's turned out to be scientifically significant, and ESO had missed it due to scheduling inertia, the press would not be kind. But science doesn't run on optics. It runs on policy. And policy said that target of opportunity requests needed to meet specific criteria: transient phenomena, high scientific impact, and no viable alternative observing strategy. The problem was that 3 Atlas wasn't a supernova or a gamma-ray burst. It was moving, yes. It was unusual, yes. But was it urgent enough to justify bumping 3 separate observing programs? Dr. Annika Roth, one of the displaced PIs, was not thrilled. "I've been waiting 8 months for this sphere time," she said during the video call. "We're studying the disk structure around a T Tauri star. If we miss this window, the star moves out of optimal sky position for another year." Hartman understood. He also understood that if ESO didn't observe 3I Atlas, and the object turned out to be truly anomalous, the scientific community would ask why the largest optical telescope in the southern hemisphere had been pointed at a T Tauri star instead. "We're not canceling your program," Hartman said carefully. "We're asking if you'd be willing to swap nights. You take the 14th. Mendez takes the 10th. Same total hours." Roth was silent for a moment. "And if the weather is bad on the 14th, we'll add a backup night." "Where?" "The schedule is full." Hartman didn't have a good answer for that. Meanwhile, on the other side of the Atlantic, a similar drama was unfolding at the Space Telescope Science Institute in Baltimore, home of the Hubble Space Telescope's scheduling operations. Dr. Jerome Fletcher had submitted a director's discretionary time request for Hubble to observe 3I Atlas using the Wide Field Camera 3 in UVIS mode. The goal was simple: get the highest resolution optical images possible and resolve the object's shape, rotation state, and surface properties. Hubble's schedule was even more contentious than VELT's. The telescope was 35 years old, operating well beyond its intended lifetime, and every hour of observing time was precious. Director's discretionary time was reserved for genuinely extraordinary circumstances: supernovae, gravitational wave counterparts, suddenly active asteroids. Using it for an interstellar object that wasn't visibly outgassing was a tough sell. Fletcher's request was reviewed by the DD Time Committee on September 8. The meeting lasted 40 minutes. The decision came down to a single question: was 3I Atlas extraordinary enough? Dr. Lisa Park, a planetary scientist on the committee, argued yes. "We've only ever had 2 interstellar objects pass through the inner solar system. Both were scientifically transformative. If this one is behaving anomalously, we can't afford to miss it. This is exactly what DD time is for." No mibano, trematamanabi. Dr. Raymond Coe, an extragalactic astronomer, disagreed. Anomalous according to whom? One deceleration measurement that could easily be a systematic error. We've seen how this plays out. Remember, Oumuamua. Half the community spent 3 years chasing a possible alien probe, and it turned out to be a comet with weird outgassing. Let's wait for more data before we start reallocating Hubble. Lenundan. Why? The vote was 4-3 in favor of approving the request. But approval came with conditions. Only 6 orbits, only in the event that ground-based observations confirmed the anomaly, and only if the object remained above magnitude 23. If it faded, the time would be reallocated. Fletcher took the deal. 6 orbits was enough. Maybe. By September 9th, the political machinery had ground forward. ESO had managed to swap observing nights with 2 programs, and delay a third. Hubble had conditionally approved 6 orbits pending further confirmation. And the Very Large Array in New Mexico had agreed to add 3E Atlas to an existing radio survey, giving it 4 hours of L-band observation starting September 11th. But the delays had cost time. Days had passed. The object was still moving. And every day that passed brought it closer to the sun, deeper into the zone where solar radiation would begin altering its surface chemistry. The pristine interstellar state was degrading, hour by hour. Dr. Mendez sent a status update to the international collaboration that had formed around 3i and Atlas. The message was blunt. We got the time, but we almost didn't. If this had happened a month earlier or a month later, we'd have missed it entirely. The system is not built for this. She was right. Humanity's astronomical infrastructure was extraordinary. The LT, Hubble, the VLA, Gemini, Keck, Subaru. Dozens of smaller telescopes and space missions, all producing torrents of data every night. But it was also fragmented, bureaucratic, and slow. Discovery moved faster than policy. Anomalies didn't wait for committee votes. And by the time the telescopes were finally pointed at 3E Atlas, part of the story had already been lost. Dr. Elena Vasquez in Hawaii summed it up in a message to her colleague. We almost didn't get to look. That's the part no one will write in the paper. We almost didn't get to look. But they did. Barely. And now, the data was coming in. This is not science fiction. This is September 2025. Chapter 3. September 9th. A spectrum with missing colors. The first X-shooter spectrum arrived just after midnight, Universal Time. Dr. Carla Mendez was asleep in Madrid when the automated email hit her inbox. The subject line read, VLT data transfer complete. Target 3i Atlas. She woke at 6:15 a.m., made coffee, and opened the file. The spectrum looked normal at first. A faint continuum sloping gently from blue to red, punctuated by a handful of weak absorption features and a few tentative emission lines. Nothing dramatic. Nothing that screamed anomaly. But Mendez had been analyzing spectra for 20 years. She knew what to look for. She opened a comparison window and loaded the spectrum of 2I Borisov, the most recent well-studied interstellar comet. Borisov had been a textbook object, rich in carbon monoxide, cyanogen, and water vapor, with clear dust scattering signatures and a well-behaved coma. It had looked like a comet from the Oort cloud, compositionally indistinguishable from solar system natives. That was the surprise. Interstellar, but not alien. Familiar. 3i Atlas was not familiar. The first thing Mendez noticed was the absence of the CN bandhead at 388 nanometers. Cyanogen, a diatomic carbon-nitrogen molecule, was one of the most common emissions in active comets. It was a proxy for volatile content. It told you the object was sublimating, shedding gas, behaving like a comet should. 2I Borisov had shown strong CN emission. So had every active comet Mendez had ever observed. 3i Atlas showed none. She checked the wavelength calibration. Correct. She checked the signal-to-noise ratio. Low, but adequate. She zoomed in on the region where the CN bandhead should have been. Flash, taut. No emission. No absorption. Just continuum. Okay, she muttered. Maybe it's not outgassing CN. Maybe it's depleted in nitrogen. That was unusual but not impossible. Some comets had low nitrogen content, but they usually compensated with other volatiles. She scrolled to the C2 Swan bands at 470 and 515 nanometers, another standard cometary emission, this one from diatomic carbon. Also, absent. She checked for C3, also absent. She checked for NH22, another nitrogen-bearing molecule. Nothing. She sat back and stared at the screen. Either this object was not outgassing at all, which contradicted the non-gravitational deceleration, or it was outgassing something invisible. Molecular hydrogen, maybe. Or helium. But those didn't produce thrust efficiently unless you were expelling them at high velocity, and there was no evidence of a high-velocity jet. Mendez called Dr. Aisha Malik at La Palma. Malik was a spectroscopist, one of the best, and she had access to the full archive of cometary spectra from the Isaac Newton Group telescopes. I need you to look at something, Mendez said. Malik pulled up the file. She was quiet for a long time. Where's the CN? She finally asked. That's what I want to know. And the C22? Gone. Carla, this doesn't look like a comet. I know. It looks like a dead asteroid. I know. Except asteroids don't decelerate. Malik ran a quick comparison with several Oort cloud comets. Hale-Bopp, Hyakutake, C 2019, Yai-4 All of them showed rich molecular emission. All of them had the standard cometary cocktail of CN, C2, C3, O, NHT2. 3 Atlas had none of it. What about the carbon chains? Malik asked. Is there any evidence of polyatomic carbon? Mendes zoomed in on the blue end of the spectrum. There was a faint, broad absorption feature around 430 nanometers. Not a clean emission line. Not a standard molecular band. Just a shallow dip in the continuum, barely 2 sigma above the noise. Maybe, Mendes said. But if it is carbon, it's not in the form we usually see. Malik pulled up a spectral atlas of carbonaceous asteroids, C-type objects rich in organic compounds. Some of them showed broad, featureless absorption in the blue due to complex aromatic hydrocarbons. The feature in 3 Atlas was similar. But that raised more questions than it answered. If this thing is carbon-rich, Malik said slowly, why isn't it outgassing carbon? CN and C2 should be all over this spectrum. Maybe the carbon is locked up, Mendes suggested. Refractory organics. Stuff that doesn't sublimate easily. Then what's producing the thrust? Silence. Mendes sent the spectrum to Dr. Mikhail Sokolov at JPL with a one-line message. We have a problem. Sokolov's reply came 3 hours later. He had run the spectrum through a suite of radiative transfer models, trying to fit the observed continuum and derive a surface composition. The best fit required a surface dominated by carbonaceous material with very low volatile content, less than 1% by mass. That was consistent with the absence of CN and C2. But it made the deceleration impossible to explain. If it's that refractory, Sokolov wrote, it shouldn't be outgassing at all. And if it's not outgassing, where's the thrust coming from? By September 10th, the anomaly had been independently confirmed by 2 other groups. Dr. Ramon Sikora at the University of Arizona obtained a medium-resolution spectrum using the Gemini multi-object spectrograph, and he saw the same thing. No CN, no CN, no CE2, weak and ambiguous carbon absorption. Dr. Hannah R. at Caltech ran a comparative analysis using archived spectra of 15 interstellar comet candidates, objects with loosely bound orbits that might have originated outside the solar system. None of them looked like 3I Atlas. This is the most chemically inert comet I've ever seen, Orr said during a hastily convened teleconference. It's like someone took a comet and baked all the volatiles out of it. Baked it where? Mendes asked. In interstellar space? Or earlier? During formation? Yeah, right. Then, it's not a comet. It's a rock. Rocks don't decelerate. The conversation went in circles. Every explanation created a new contradiction. If 3I Atlas was volatile rich, why was the spectrum so barren? If it was volatile poor, why was it decelerating? If it was outgassing, why couldn't they see the gas? If it wasn't outgassing, what was pushing it? And then Dr. Jerome Fletcher at STCI said something that made everyone stop. What if it's processed? The line went quiet. Processed how? Mendes asked. I don't know. UV radiation, cosmic rays, something that stripped the surface volatiles over millions of years of interstellar transit. You're left with a carbon-rich crust, maybe a few meters thick, covering a still volatile interior. The surface looks dead, but underneath, it's still active. It was plausible. Interstellar space was not benign. UV photons from distant stars, high-energy cosmic rays, and charged particles from the interstellar medium all bombarded objects over geological timescales. A comet drifting through interstellar space for 1 million years would accumulate significant radiation damage. The surface could be desiccated, carbonized, stripped of anything volatile. But beneath that crust, pristine ices could remain intact. If that's true, Sokolov said, we should see evidence of outgassing once the crust fractures. Heat it up enough, the pressure builds underneath, and eventually something breaks. Well, done. Or said quietly, the crust doesn't fracture. It stays intact. And the outgassing happens through subsurface vents we can't resolve. That would explain the invisible thrust. If gas was escaping through narrow channels deep within the object, it might not form a visible coma. It would just vent into space, diffuse and undetectable, but still producing thrust. Mendes liked the idea. It was neat. It was physical. It didn't require anything exotic. But it also couldn't be tested. Not yet. They'd need radar. They'd need thermal imaging. They'd need resolution they didn't have. She stared at the spectrum again. The missing CNN. The absent C2 dye. The faint, ambiguous absorption that might be complex organics or might be noise. We're looking at the surface, she said. But the answer isn't on the surface. It's underneath. No one disagreed. But no one knew how to see beneath it either. This is not science fiction. This is September 2025. Chapter 4. September 12th. The solar system's growing surveillance net. While astronomers wrestled with the spectrum of 3A Atlas, the rest of the solar system was moving forward. September 12th, 2025, was a busy day in space. At 11:42 UEC, the James Webb Space Telescope completed its quarterly attitude adjustment, reorienting itself to point toward a new section of sky near the constellation Cetus. Webb had been operational for over 3 years now, and it had fundamentally changed the way humanity studied the universe. Its infrared vision could pierce through dust clouds, resolve the atmospheres of distant exoplanets, and peer back to the earliest galaxies formed after the Big Bang. But Webb was not looking at 3I Atlas. Not yet. The telescope's observing schedule was planned months in advance, and barring a genuine emergency, it didn't deviate. 3 Atlas was scientifically interesting, yes. But it wasn't a supernova. It wasn't a gravitational wave counterpart. It was an anomalous comet, and anomalous comets didn't make the cut for directors' discretionary time. Not unless something truly extraordinary happened. So Webb continued its scheduled program, a deep survey of high redshift galaxies, a spectroscopic campaign targeting the atmospheres of 3 super-Earths, orbiting nearby red dwarfs, and a detailed study of the ice composition on Europa. Jupiter's study of the ice composition on Europa. Ocean-bearing moon. All critical science. All important. But none of it involved the small, faint, chemically inert object currently slowing down as it approached the sun. On the same day, Starship Flight Test 12 was delayed again. SpaceX's fully reusable Super Heavy launch vehicle had been promised to revolutionize access to space. At 121 meters tall and capable of lifting over 100 metric tons to low Earth orbit, Starship was the largest rocket ever built. It was supposed to carry astronauts to the moon, enable the colonization of Mars, and make spaceflight routine and affordable. But it was also a nightmare of regulatory approval, engineering setbacks, and public spectacle. Flight Test 11 in August had ended with a successful booster catch, but a failed second stage landing. The heat shield had burned through during re-entry, and the vehicle had broken apart over the Pacific. No one was hurt. Nothing was lost except the prototype and another 3 months of schedule. The next test was now slated for mid-October, pending FAA clearance and range availability. The delay frustrated engineers at JPL and elsewhere, who had been hoping Starship could eventually be used for rapid response science missions. Imagine detecting an interstellar object and launching a probe to intercept it within weeks, not years. Imagine getting a spacecraft to 3I Atlas while it was still pristine, before solar radiation started altering its surface. That kind of capability didn't exist yet. But it was close. Tantalizing close. Just not close enough. Meanwhile, at NASA's Goddard Space Flight Center, engineers were preparing for the next phase of the Nancy Grace Roman Space Telescope's integration and testing. Roman, often called Hubble's successor, though that title truly belonged to Webb, was a wide-field infrared survey telescope designed to study dark energy, exoplanets, and the structure of the Milky Way. Its primary mirror was the same size as Hubble's, but its field of view was 100 times larger. One image from Roman would cover as much sky as 100 Hubble images stitched together. Roman was scheduled to launch in May 27, if it stayed on schedule, which it probably wouldn't. But when it did launch, it would have the capability to discover interstellar objects in unprecedented numbers. Its wide-field survey mode would scan enormous swaths of sky every few days, and its sensitivity to faint, fast-moving objects would make it the ultimate interstellar hunter. Estimates suggested Roman could detect dozens of interstellar visitors per year, maybe more. But that was 2027. This was 2025. And the interstellar visitor currently in the solar system was observable now, with the tools humanity had now, which were powerful but fragmented. Dr. Elena Vasquez thought about that a lot. She had spent the last week coordinating observations from half a dozen different facilities. Atlas in Hawaii, Gemini North, the VLT in Chile, the Vela in New Mexico, and now Hubble. Each one had its own scheduling system, its own proposal process, its own data pipeline. There was no centralized command structure, no unified interstellar object response protocol. It was all ad hoc. Email chains, Slack channels, hastily arranged Zoom calls. It worked, barely, but it was inefficient, and inefficiency meant lost opportunities. Vasquez had drafted a proposal once, years ago, for an interstellar object rapid response network. The idea was simple: a standing agreement among major observatories to allocate a small percentage of their time, maybe 2%, to a shared pool that could be activated immediately upon detection of a high-priority transient target. Interstellar objects, near-Earth asteroids on collision trajectories, supernovae within 10 megaparsecs, gravitational wave, optical counterparts. The proposal had been politely declined. Too complicated, too much coordination, too many competing priorities. Now, staring at the patchwork observation schedule for 3I Atlas, Vasquez wondered how many discoveries had been missed because the telescopes were pointed the wrong way. Elsewhere in the solar system, other eyes were watching. The Hubble Space Telescope, still operational after 35 years, was imaging distant galaxies and refining measurements of the universe's expansion rate. The Chandra X-ray Observatory was studying supermassive black holes and the hot gas surrounding galaxy clusters. The Transiting Exoplanet Survey satellite was scanning thousands of stars for the telltale dip in brightness that indicated a planet crossing in front. And closer to home, a small fleet of Mars orbiters, NASA's MAVEN and Mars Reconnaissance Orbiter, ESA's Trace Gas Orbiter, and China's Tianwen-1, were mapping the red planet in exquisite detail, searching for signs of ancient water, monitoring seasonal dust storms, and preparing the ground for future human missions. None of them were looking at 3 Atlas, because the surveillance net, impressive as it was, remained focused on known targets: planets, galaxies, stars. The architecture of observation was designed for objects that didn't move, or moved predictably. Interstellar visitors were interlopers. They appeared without warning, moved fast, and disappeared before most telescopes could react. On September 13th, Dr. Carla Mendez sent an email to the International Astronomical Union's Working Group on Small Body Nomenclature. The subject line was, "We need a better system." The email was blunt. She outlined the delays in securing telescope time, the fragmentation of observational resources, the lack of a coordinated response plan. She proposed establishing a formal interstellar object protocol, predefined criteria for triggering emergency observations, a rotating pool of backup telescope time, and a centralized data repository where all observations would be immediately shared. The response was polite, but non-committal. "Thank you for your input. We will discuss this at the next committee meeting in November." November, 2 months away. 3 Atlas would be long gone by then. Mendez closed her laptop and walked to the window. Outside, Madrid was bright and warm under the midday sun. Somewhere out there, 55 million kilometers away, a small dark object was drifting silently through the inner solar system, carrying secrets that no one had quite figured out how to read. The telescopes would eventually turn. The data would eventually come. The answers would eventually emerge. But not as fast as the questions. This is not science fiction. This is September 2025. Chapter 5. September 14th. The Green Ion Line. The email from Dr. Ayesha Malik arrived at 3:47 a.m. Madrid time. Subject line: "You need to see this." Dr. Carla Mendes woke up 4 hours later and opened it. Attached was a high-resolution spectrum from the William Herschel telescope at La Palma, captured during a 6-hour integration on the night of September 13. The exposure had been deep, pushing the signal-to-noise ratio to the limit, trying to squeeze every photon out of the faint, distant object. And there, sitting at 557.7 nanometers, was a narrow emission line that shouldn't have been there. It was faint. Maybe 3 sigma above the noise. But it was real. And it was unmistakably ionized oxygen, the forbidden 2OI line, a spectral signature commonly seen in cometary tails, planetary nebulae, and the upper atmospheres of auroral zones on Earth. It was what gave Earth's auroras their characteristic green color. But here's the problem. The line was pointing the wrong way. Mendes stared at the spectrum for a full minute before calling Malik. "Where is this line coming from?" she asked. "That's the question," Malik replied. "It's not in the coma. There is no coma. It's in the tail." "What tail?" "Exactly." Mendes pulled up the most recent imaging data from Gemini North. The object looked like a point source. No visible tail, no extended structure. Just a faint dot against the background stars. But cometary ion tails were often invisible in broadband imaging, especially if they were faint. You needed narrowband filters tuned to specific emission lines to see them. And until now, no one had thought to look. "Did you image it?" Mendes asked. "We tried. Last night. Used a narrowband filter centered on 558 nanometers. 2-hour exposure. And there's structure. Faint, but it's there. I'm sending you the file now." Window down. Mendes waited. 30 seconds later, the image appeared on her screen. At first, it looked like noise. A grainy field of black and gray, with a single bright pixel near the center. But when Mendes adjusted the contrast and stretched the scale, she saw it. A faint, elongated streak extending from the object, roughly 20 arcseconds long, oriented at an angle of about 73 degrees east of north. It was a tail. An ion tail, glowing faintly in the green light of forbidden oxygen. "Okay," Mendes said. "So it does have a tail. Why didn't we see this before?" "Because it's incredibly faint. And because we weren't looking for it. But here's the thing, Carla. The tail is pointing in the wrong direction." Mendes pulled up a quick solar wind model. Ion tails were shaped by the solar wind, the constant stream of charged particles flowing outward from the sun. The tail should point directly away from the sun, following the magnetic field lines embedded in the solar wind. It was one of the most predictable features in cometary physics. She overlaid the expected solar wind direction on the image. The tail was offset by 11 degrees. "That's not possible," Mendes said. "I know. Solar wind doesn't bend like that." "I know." Mendes rechecked the geometry. She verified the object's position, the sun's position, the date and time of the observation. She ran the solar wind model again, with different input parameters. Higher velocity, lower density, variable magnetic field strength. Nothing worked. No matter how she adjusted the model, the tail refused to align with the predicted solar wind direction. The offset was too large to be a measurement error. It was too consistent to be noise. And it was too improbable to be random. Dr. Mikhail Sokolov, at JPL, ran the numbers. The probability of a solar wind-driven ion tail randomly misaligning by 11 degrees, given known variations in solar wind speed and interplanetary magnetic field direction, was roughly 1 in 20,000. Not impossible, but deeply unlikely. Could there be a local magnetic field? Sokolov asked during the teleconference on September 15. "From what?" Mendes replied. "The object itself? If it had a magnetosphere, the solar wind would interact with it asymmetrically. You could get a tail offset." "Oh, comets don't have magnetospheres. This isn't behaving like a comet." Mendes didn't have a response to that. Dr. Hannah R. at Caltech proposed an alternative. What if it's not a solar wind tail, What if it's a dust tail illuminated by resonance scattering? It's too narrow, Malik said. Dust tails are diffuse. This is linear, and the spectrum shows ionized oxygen, not scattered sunlight. Then maybe it's outgassing asymmetrically. A jet, angled off the sun-facing side. The gas gets ionized, forms a tail, but the thrust from the jet creates a torque that rotates the tail direction. It was creative, but the math didn't work. To produce an 11-degree offset, the outgassing jet would need to be producing a torque orders of magnitude larger than what the observed tail emission could support. You'd need either an enormous jet, which would be easily visible, or an impossibly efficient ionization mechanism. By September 16th, 3 more independent observations had confirmed the tail's existence and orientation. Dr. Jerome Fletcher obtained Hubble imaging in the 555 dB filter, which was centered almost exactly on the Keophar emission line. The tail was there, faint but unmistakable. Dr. Ramon Sikora at the University of Arizona used the Large Binocular Telescope to image it in narrowband. Same result? Same offset. The data was consistent. The tail was real, and it was pointing the wrong way. Dr. Vasquez in Hawaii ran a statistical analysis. She pulled archival data from 200 comets observed over the past 30 years and calculated the distribution of tail angles relative to the expected solar wind direction. The standard deviation was about 3 degrees. Outliers occasionally reached 6 or 7 degrees, usually due to transient solar wind disturbances or complex outgassing geometry. An 11-degree offset fell outside the 99.7th percentile. It was a 4 sigma anomaly. This is not a normal comet, Vasquez wrote in her observing log. This is not a normal tail, and if it's not solar wind, and it's not outgassing, then what is it? One possibility, never spoken aloud but quietly written in private notes, was that the tail wasn't random, that the alignment wasn't an accident, that the 11-degree offset corresponded to something, a direction, a target, a signal. Dr. Fletcher ran a quick astrometric check. He calculated the direction the tail was pointing, projected it backward through space, and asked, if this tail were aimed at something, what would it be aimed at? The answer was nowhere. Empty space. No bright stars, no nearby planetary systems, no interesting radio sources. Just the void between constellations, unremarkable and silent. Fletcher deleted the calculation. Then he ran it again, just to be sure. Same result. Nothing. But the tail was still there. Still glowing. Still pointing 11 degrees away from where it should. On September 17th, Dr. Malik sent one final message to the group. We need to stop calling this a comet. No one disagreed. This is not science fiction. This is September 2025. Chapter 6, September 17th. When instruments disagree. By mid-September, the data was piling up. And it was contradictory. On September 17th, Dr. Elena Vasquez sat in her office in Hawaii, surrounded by printouts of observation reports, spectroscopic plots, astrometric tables, and photometric light curves. She had taped them to the walls, arranged them chronologically, color-coded by instrument. It looked like the workspace of someone trying to solve a crime. In a sense, she was. The problem was simple. Every telescope was telling a different story. The Very Large Array had observed 3EI Atlas on September 11th and 12th, using the L-band receivers to search for molecular emission at radio wavelengths. The goal was to detect carbon monoxide, one of the most common molecules in cometary coma and one of the easiest to observe in the radio spectrum. Co-emits strongly at 115 GHz, and the Valet was sensitive enough to detect it even in faint, distant objects. The result? Nothing. No CO emission. No emission at any frequency. The object was radio silent. That was strange. Even inactive comets sometimes show faint co-emission if they're cold enough and far enough from the sun. But 3 Atlas, which was decelerating and presumably outgassing, showed absolutely nothing. Dr. Carlemande had expected that. The optical spectra had already shown an absence of CN and C2, so the lack of CO wasn't surprising. But it was frustrating. Every time they looked for gas, they found none. Every time they looked for dust, they found none. Yet the object was slowing down, and now it had an ion tail. Something was happening. They just couldn't see it. Meanwhile, Hubble's imaging data was equally confusing. Dr. Jerome Fletcher had received the processed images from the Wide Field Camera 3 on September 15. 6 orbits, split across 2 visits, capturing the object in 4 filters: FAO 130 AU blue, 555 DU green, FATE 114 W near infrared, and F 350 UV. The goal was to measure the object's color, brightness, and rotation state. The images were exquisite. Hubble's resolution was unmatched, even 35 years after launch. The object appeared as a clean, well-sampled point source with no visible coma, no dust tail, no extended structure. Just a single bright pixel against the black. But the photometry didn't make sense. In the F555 view filter, the green band centered on 555 nanometers. The object was brighter than expected. Significantly brighter. About 0.3 magnitudes, which corresponded to a factor of 1.3 in flux. That doesn't sound like much, but in astronomical terms, it's huge. A 30% brightness excess in a single band suggests either unusual surface composition or active emission. Fletcher checked the calibration. Correct. He checked for scattered light from nearby stars. None. He checked for cosmic ray hits. Clean data. The excess was real, and it was only in the green band. In the blue and near-infrared filters, the object's brightness matched the predictions from the optical light curve. It was behaving like a normal, inert object reflecting sunlight. But in the green band, centered almost exactly on the wavelength of the TOAI ion emission line, it was glowing. "This is the tail," Fletcher said during a call with Mendez. "We're seeing emission, not reflection." "But there's no spatial extent," Mendez replied. "Hubble should resolve a tail if it's bright enough to boost the photometry. Not if the tail is too faint or too narrow. We might be seeing integrated emission from a very thin structure. Then why doesn't the spectroscopy show it more clearly?" Fletcher didn't have a good answer. The contradiction deepened when the light curve analysis came back. Dr. Ramon Sikora, at the University of Arizona, had been monitoring 3A Atlas photometrically for 2 weeks, taking short exposures every night to measure the object's brightness as a function of time. Comets and asteroids often show periodic brightness variations due to rotation. A non-spherical object spins, and as different parts of its surface come into view, the amount of reflected light changes. By measuring the period and amplitude of these variations, you can infer the object's shape, spin rate, and surface properties. Sikora's light curve showed a clear periodic signal with a period of 8.3 hours and an amplitude of 0.15 magnitudes. That suggested an elongated body, maybe 1.5 to 1 axis ratio, rotating once every 8.3 hours. Completely normal. Except the period was changing. Between September 10th and September 17th, the rotation period had decreased by 0.07 hours. The object was spinning faster. That shouldn't happen. Rotation periods can change due to outgassing torque. If gas jets fire asymmetrically, they can spin the object up or down. But 3I Atlas wasn't showing visible outgassing. And even if it were, the torque required to change the rotation period by that much in 1 week would produce obvious jets and a measurable coma. "This is consistent with internal mass redistribution," Sikora said during a group discussion. "If the object is losing mass from one side, or if there's subsurface activity, the moment of inertia could change, and that would alter the spin rate. But we're not seeing mass loss," Mendez pointed out. "No dust, no gas, no coma. Not in the optical, but maybe it's there, just below detection threshold." It was plausible. Barely. But it required an outgassing rate so low that no instrument could detect it, yet strong enough to spin up a multi-kilometer object. The numbers were hard to reconcile. Then there was the thermal data. Dr. Hannah Orr at Caltech had obtained infrared observations using the MERCI instrument on NASA's Infrared Telescope facility in Hawaii. MUSI observed in the mid-infrared, around 10 micrometers, where thermal emission from solar-heated surfaces is strongest. By measuring the infrared brightness, you can estimate the object's size, temperature, and thermal inertia, how quickly it heats up and cools down. The data was strange. The object's temperature was lower than expected. At 3I Atlas's current distance from the Sun, about 140 U, a bare rock should be around 220 Kelvin, assuming moderate albedo. But the measurements showed 190 Kelvin. Too cold. As if the surface wasn't absorbing as much sunlight as it should. Aura ran thermal models with different albedos. High albedo objects, bright, reflective surfaces, absorb less sunlight and stay cooler. But to get the observed temperature, the albedo would need to be around 0.5, which is unusually high for a comet or asteroid. Most small bodies have albedos between 0.03 and 0.15. Only icy objects like Enceladus or Europa have albedos that high. But 3I Atlas didn't look icy. The optical spectrum showed no water-ice absorption features. No surface frost. No reflectance signature consistent with ice. Maybe the surface is covered in something else, or suggested. Bright organics. Sulfur, tortar. Saltsteinelane. Nindbordiamishat. Nine. Diamondstone. Or it's not in thermal equilibrium, Sokolov offered. If the surface is rapidly losing heat through sublimation or radiation, it could stay cooler than steady-state models predict. But not detecting sublimation. Then maybe it's subsurface, internal heat loss that doesn't show up as gas emission. The explanations were multiplying faster than the data. Every new observation added a piece to the puzzle, but the pieces didn't fit together. The radio silence contradicted the ion tail. The photometric excess contradicted the lack of spatial extent. The thermal anomaly contradicted the optical spectrum. The spin-up contradicted the absence of visible outgassing. On September 18th, Dr. Vasquez printed out a summary table and taped it to the wall. Instrument, observation, implication, contradiction. Vla, no radio emission, no outgassing, deceleration, ion tail. Hubble, green photometric excess. Active emission, no resolved tail. Light curve, rotation spin-up, outgassing torque, no visible gas. RTF, low thermal emission, high albedo or cooling, no ice signature. OLT, no CN, no C2, inert surface, deceleration tail. She stared at it for a long time. Then she wrote in red marker at the bottom, "What are we missing?" No one had answered yet. This is not science fiction. This is September 2025. Chapter 7, September 20th. A shape revealed only by absence. The shape of 3 Atlas was not visible. Not directly. It was too small, too far away, too faint. Even Hubble, with its extraordinary resolution, couldn't resolve the object's structure. It appeared as a single pixel, a point of light indistinguishable from a distant star. But shape can be inferred, not by looking at what's there, but by measuring what's missing. On September 20th, Dr. Ramon Sikora at the University of Arizona published an updated light curve analysis. He had combined 3 weeks of photometric observations from 5 different telescopes: Gemini North, the ELT, the Large Binocular Telescope, the Lowell Discovery Telescope, and his own team's data from Kitt Peak. Together, they covered nearly continuous monitoring of 3I Atlas from September 3rd to September 19th, with brightness measurements taken every few hours. The light curve was complex, not a simple sinusoid, not a smooth, periodic rise and fall. It showed multiple peaks and valleys, asymmetric maxima, and a subtle but persistent secondary periodicity that hinted at something more than just a rotating ellipsoid. Sikora ran shape models. The standard approach is to assume a triaxial ellipsoid, a football-shaped object with 3 different axis lengths, and vary the dimensions, spin rate, and viewing geometry until the predicted light curve matches the observed one. It's not a perfect method. Many different shapes can produce similar light curves, but it gives you a starting point. One way. The best fit model suggested an elongated object with axis ratios of roughly 2.1.31, longer and thinner than Oumuamua, which had been about 10.1, but still distinctly non-spherical. The spin period was 8.31 hours, now well constrained, and the spin axis was tilted at about 65 degrees relative to the ecliptic plane. But the fit wasn't great. The residuals, the difference between the model and the data, showed systematic structure. The observed light curve had bumps and dips that the smooth ellipsoid model couldn't reproduce. Something was wrong. Sikora tried more complex models, ellipsoids with surface features, contact binaries, rubble piles, fractured bodies with voids. The fractured model worked better. When he introduced internal voids, empty spaces within the object where no surface reflected light, the model-like curve started matching the observations. The idea was simple. If 3I Atlas wasn't a solid chunk of rock or ice, but rather a fragmented structure with gaps, cracks, and hollow regions, the reflected light would behave differently. Some orientations would show more surface area. Others would show less. The brightness would vary in asymmetric, non-sinusoidal ways. The best fit fractured model suggested an object with roughly 18% porosity. Nearly 1/5 of its volume was empty space. Sikora sent the results to Dr. Elena Vasquez. Her reply came within minutes. Is this consistent with a collision? Sikora thought about it. Porosity was common in asteroids. Most small bodies weren't solid. They were rubble piles, collections of smaller fragments loosely bound by gravity, with voids between the pieces. But collision-derived rubble piles usually had porosities closer to 40% or 50%, and they tended to be rotationally unstable. Spin them too fast and they fly apart. 3. Atlas was spinning at 8:30 hours, which was relatively fast but not extreme. And it wasn't showing signs of breakup. Maybe it's not a rubble pile, Sikora replied. Maybe it's fractured but still coherent, like a single body that's been stressed, cracked, but not shattered. Vasquez liked that idea. Stress fractures implied history. They told a story. If 3 Atlas had cracks and voids, something had put them there. Thermal stress, maybe. Or tidal forces during a close encounter with another object. Or internal pressure from subsurface outgassing. Or something else. Dr. Carla Mendez ran a tidal stress analysis. If 3I Atlas had passed close to a star or a planet during its journey through interstellar space, the gravitational gradient, the difference in gravity from one side of the object to the other, could have deformed it, stretched it, and introduced fractures. She calculated the minimum distance required to produce the observed porosity. The answer depended on the object's composition. If it was solid ice, you'd need a close pass within about 50,000 kilometers of a sun-like star. If it was rock, more like 20,000 kilometers. If it was already weakened by previous fractures, maybe farther. But there was no way to know. The object's history was invisible. All they had was the present state, fractured, porous, and spinning. Dr. Wei Hannah Orr at Caltech proposed an alternative explanation. What if the voids aren't from fractures? She said during a video call. What if they're chambers? The word hung in the air. Chambers like what? Sikora asked. Like cavities. Hollow spaces. If this thing formed in a low-gravity environment, outgassing could have carved out subsurface voids over time. Gas escapes through cracks, leaves behind empty space. You'd get a structure that's partly solid, partly hollow. That's not how comets form, Mendez said. This isn't behaving like a comet. It was becoming a refrain. Every conversation about 3I Atlas circled back to the same point. Normal explanations didn't fit. The object resisted categorization. It looked like a rock, but moved like a comet. It had a tail but no coma. It was cold, but not icy. And now it was fractured but not fragmented. Dr. Jerome Fletcher, who had been quiet during most of the discussion, finally spoke. What if we're looking at this backward? Backward how? Vasquez asked. We keep assuming the shape is natural, random, a product of formation or collisions or thermal stress. But what if it's not? What if the geometry is deliberate? No one said anything. Fletcher continued. I'm not saying it is. I'm saying we can't rule it out. If you wanted to build an interstellar probe, you wouldn't make it spherical. You'd make it elongated to minimize cross-section during transit. You'd include internal voids to reduce mass and increase insulation. And you'd make it tumble to evenly distribute thermal load. Or, Mendes said carefully, you'd have an elongated, fractured comet nucleus that formed naturally in a protoplanetary disk, got ejected during planetary migration, spent 10 million years drifting through interstellar space, and happened to pass it through our solar system while we were watching. Right, Fletcher said. Occam's razor. The simpler explanation. Except the simpler explanation doesn't fit the data. Neither does the complex one. The conversation ended there. Because both were right. The natural explanation required too many coincidences. The artificial explanation required too much speculation. And the data, maddeningly, supported neither and contradicted both. On September 21st, Sikora published the fractured shape model on ArcSeeFTite. The paper was titled Photometric Analysis of Interstellar Object 3I Atlas, Evidence for a Porous, Elongated Structure. The conclusion was cautious. The observed light curve is best fit by a fractured porous body with axis ratios of AA2, 1 and 18% void fraction. The origin of this structure remains uncertain. Possibilities include tidal disruption, thermal cracking, or subsurface outgassing. Further observations, particularly radar or high-resolution imaging, are required to constrain the geometry and internal structure. He didn't mention the other possibility, the one Fletcher had raised, the one no one wanted to write down, because once you wrote it down, it became part of the record, part of the discourse. And the discourse around interstellar objects was already fragile enough. But the voids were there. The fractures were there. The geometry was there, revealed only by the light that didn't return. This is not science fiction. This is September 2025. Chapter 8. September 23rd. The Politics of Looking Longer. The email from NASA headquarters arrived on September 23rd at 9:15 a.m. Eastern Time. Subject: Hubble Extended Mission Time. Request denied. Dr. Jerome Fletcher opened it in his office at the Space Telescope Science Institute and felt his stomach sink. He had submitted a request for an additional 12 orbits of Hubble observation time to continue monitoring 3 Atlas. The original 6 orbits had been valuable. They'd confirmed the green photometric excess, refined the astrometry, and constrained the object's rotation state. But they'd also raised new questions. Questions that needed more data, more exposure time, more resolution. The request had been reviewed by the mission office. The response was polite, but final. Due to competing priorities, including scheduled observations of the Hubble Ultra Deep Field Continuation Program, the James Webb Alignment Verification Campaign, and maintenance downtime for gyroscope health checks, we are unable to allocate additional director's discretionary time for Target 3 Atlas at this time. We encourage the PI to resubmit during the next proposal cycle. The next proposal cycle was in November. By then, 3A Atlas would be deep in solar conjunction, unobservable for months, and any pristine interstellar chemistry would be long gone. Fletcher closed the email and stared at the ceiling. It wasn't personal. It wasn't malicious. It was just policy. Hubble was the most oversubscribed telescope in history. Every hour of observation time was fought over by hundreds of astronomers, each with compelling, urgent, transformative science. Galactic archaeology, exoplanet atmospheres, supernova cosmology, gravitational lens measurements, black hole accretion. All of it mattered. All of it was important. But only some of it could actually be observed. And 3I Atlas, strange as it was, didn't make the cut. Fletcher forwarded the email to Dr. Elena Vasquez in Hawaii and Dr. Carla Mendez in Madrid. Bye. Vasquez replied first. Damn it. Mendes replied second. Can we appeal? Fletcher typed a response but didn't send it, because he knew the answer was no. Appeals required extraordinary justification, a genuine, unambiguous, scientifically transformative discovery. Not an anomaly, not an inconsistency, a discovery. And 3i Atlas, for all its strangeness, wasn't that. Not yet. Meanwhile, a similar drama was unfolding at the European Southern Observatory. Dr. Mendes had requested an extension of the ELTE observation program. She wanted another 8 hours on X-shooter to obtain deeper, higher signal-to-noise spectra, and 4 hours on sphere to attempt direct imaging of the ion tail in multiple narrowband filters. The scientific case was strong. The object was still accessible. The data was still incomplete. The request was reviewed by the VLTA Program Committee on September 22nd. The decision came back on September 24th, denied. The reasoning was nearly identical to Hubble's: competing priorities, limited availability, and insufficient justification for displacing already approved programs. The committee acknowledged the scientific interest in 3i Atlas, but noted that the current dataset, while incomplete, is sufficient to constrain the object's basic properties and compositional characteristics. Sufficient. That word again. Mendes read the decision twice, then called Dr. Lucas Hartman, the committee chair. Lucas, we're not asking for a lot. 8 hours, that's less than one night. Carla, you know how this works. We have 17 approved programs waiting for time. Some of them have been waiting for 6 months. This object is leaving. So are the transiting exoplanets we're supposed to be observing next week. Orbital windows close. We can't prioritize one time-sensitive target over another without a clear metric. The metric is that this is only the third interstellar object we've ever seen. And it's behaving unlike anything we've cataloged. Nedis. Behaving unusually is not the same as being unprecedented. Oumuamua was unusual. We observed it. We published dozens of papers, and the consensus was that it's natural. Exotic, but natural. We don't have consensus on this one yet. Then get more data from other telescopes. We're trying. Everyone's schedule is full. Hartman was silent for a moment. Carla, I'm sympathetic. I really am. But unless this object does something undeniably extraordinary, brightens unexpectedly, emits a radio signal, breaks apart, I can't justify bumping approved science. Mendes thanked him and hung up. Then she sat at her desk and tried to figure out what undeniably extraordinary actually meant. The object was already extraordinary. It was decelerating without visible gas. It had an ion tail pointing the wrong direction. It was colder than it should be. It was spinning up without obvious torque. Every single observation was inconsistent with standard models. But none of that was undeniable, because every anomaly could be explained, barely, awkwardly, with enough caveats, as a natural phenomenon. Low-level outgassing below detection threshold. Subsurface venting. Isometric albedo dot. Magnetic field interactions. Complex thermal inertia. Unlikely? Yes. Contrived? Maybe. But possible. And possibility was enough to keep the object in the realm of normal science. Interesting, but not extraordinary. Fletcher, Mendes, and Vasquez convened a video call on September 25th to discuss options. We need a strategy, Vasquez said. We can't keep losing telescope time. We need a result, Fletcher replied. Something publishable. Something that forces people to take this seriously. We have results, Mendes said. We have a dozen anomalies. Anomalies aren't enough. We need an explanation. We don't have one. Fletcher leaned back in his chair. Then maybe we should say that. Publicly. Write a paper that says, we've observed this object extensively, and we cannot reconcile the data with any natural model we have. Not, it's artificial. Not, it's alien. Just, we don't know, and we need more time. That'll get us laughed out of peer review, Vasquez said. Will it? Or will it get us attention? The question hung there. Because attention was a double-edged sword. If they went public with a paper saying, "We don't understand this object," the media would run wild. Headlines about alien probes. Speculation about interstellar civilizations. The same circus that had surrounded Oumuamua, but louder, because this time the data was more ambiguous. And if the media storm got loud enough, it could poison the well. Serious scientists would distance themselves from the project. Funding agencies would get nervous. Peer reviewers would be harsher, more skeptical, more inclined to reject anything that smelled like sensationalism. But if they stayed quiet, the object would slip away unobserved. The data would remain incomplete. The questions would remain unanswered. And in a few years, 3E Atlas would be a footnote. A curious anomaly. A cautionary tale about the limits of observational astronomy. "We publish," Mendez said finally. "We publish everything we have. All the contradictions. All the unknowns. We make the case that this object is worth more observation, and we let the community decide." Vasquez nodded. "Agreed." Fletcher sighed. "Okay, let's write it." They started drafting the paper that night. The working title was Observational Constraints on Interstellar Object 3I Atlas, Non-Gravitational Dynamics, Anomalous Spectroscopy, and Unresolved Geometric Structure. It was dry. It was cautious. It was everything a scientific paper should be. But buried in the discussion section, near the end, they added one paragraph that wasn't cautious at all. "The ensemble of observations presented here does not fit any single natural model currently available in the literature. While individual anomalies can be explained through ad hoc hypotheses, the combined dataset resists coherent interpretation. We conclude that 3A Atlas is either composed of materials or governed by processes not yet adequately modeled, or that the object's structure and behavior are fundamentally different from any previously studied comet or asteroid. Extended observation is critical to resolve this ambiguity." They sent the draft to 10 colleagues for feedback. 3 replied with supportive comments. 2 suggested removing the final sentence as too speculative. 5 didn't reply at all. On September 27th, they submitted the paper to the Astrophysical Journal Letters. The review process would take weeks, maybe months. By the time it was published, 3E Atlas would be gone. But the data would remain. The questions would remain. And someone, someday, might have the answers. This is not science fiction. This is September 2025 Dark. Chapter 9, September 26th, The Alignment Problem. On September 26th, 2025, at 14:37 UTC, something unusual happened. Not with the object itself, but with geometry. Dr. Elena Vasquez was reviewing astrometric data when she noticed it. The positions had been updated with the latest observations from Gemini North, refining 3I Atlas's trajectory to within a few hundred kilometers. She plotted the orbit in 3 dimensions, rotating the view to see it from different angles. And then she stopped. The object's current position placed it almost exactly on the plane of the ecliptic, the flat disk in which the planets orbit the Sun. That wasn't unusual by itself. Many interstellar objects pass through the ecliptic plane. What was unusual was that Earth, the Sun, and 3I Atlas were nearly collinear. The 3 bodies formed an almost perfect straight line, with 3 Atlas positioned between Earth and the general direction of the galactic center. Vasquez checked the geometry twice. The angular separation was less than 2 degrees. That meant that if you stood on 3 Atlas and looked toward the Sun, Earth would be right there, a pale blue dot almost perfectly aligned with the star that lit it. She pulled up a galactic coordinate map. The object's trajectory, when projected backward through space, pointed loosely toward the direction of the constellation Sagittarius, roughly toward the galactic center, though not precisely. The error was about 15 degrees, which was significant. But the coincidence was still striking. Sun, Earth, object, galactic plane, all nearly aligned, all at the same moment. Vasquez calculated the probability. The ecliptic plane is thin, only a few degrees thick when you account for the inclination of most solar system bodies. The probability of an interstellar object passing through the ecliptic at any given time is roughly 5%. The probability of Earth being within 2 degrees of alignment with the object and the Sun at that moment is another 5%. The probability of this happening while the object is also within 1.50 of the Sun, close enough for detailed observation, is another 10%. Multiply them together and you get 0.025% Darjoy. 1 in 4,000. Not impossible, but unlikely. She sent the calculation to Dr. Carla Mendez with a single line. Is this worth mentioning? Mendez called her immediately. Are you sure about the geometry? Mendez asked. I've checked it 3 times. The alignment is real. Nirin. No. For how long? Vasquez ran a propagation model, advancing the orbit forward and backward in time. The best alignment was yesterday, September 25th, at around 18:00 UTC. We're moving out of it now. By October 1st, the configuration will be broken. Earth will have moved too far along its orbit. So we had a 2-day window. Roughly. Mendez was quiet for a moment. What are you thinking? Vasquez hesitated, because what she was thinking sounded absurd. But the data was right there, indifferent to how it sounded. If this object were transmitting something, a signal, a message, whatever, the best time to do it would be during a geometric alignment. Maximum efficiency, minimum path loss. You point toward the Sun, and Earth is right there in the beam. Did we detect anything? No. Then it's just a coincidence. Probably. But Vasquez didn't sound convinced, and Mendez knew why. Because probably wasn't the same as certainly. And in the context of everything else that was strange about Theory Atlas, one more improbable coincidence started to feel less like noise and more like signal. By September 27th, the alignment had propagated through the research community. Dr. Mikhail Sokolov at JPL ran an independent calculation and confirmed Vasquez's numbers. Dr. Hannah Orr at Caltech extended the analysis, checking whether the alignment had any precedent in the previous 2 interstellar objects. Onai Oumuamua had passed through the solar system in 2017, but its trajectory had been steeply inclined, about 122 degrees relative to the ecliptic. It had never come close to aligning with Earth and the Sun simultaneously. Toy Borisov, in 2019, had been closer to the ecliptic plane but had reached perihelion when Earth was on the opposite side of the Sun. No alignment. Theory Atlas was the first interstellar visitor to pass through a Sun-Earth object alignment within observable range. Was that meaningful? Or just luck? Dr. Jerome Fletcher at STCE decided to check the radio data. The Very Large Array had observed 3 Atlas on September 11th and 12th, well before the alignment. But the National Radio Astronomy Observatory also operated the Green Bank Telescope in West Virginia, which had been conducting a long-term survey of nearby stars as part of the Breakthrough Listen project, a privately funded search for extraterrestrial intelligence. Fletcher reached out to Dr. Sofia Ramirez, one of the project scientists at Breakthrough Listen. He asked if GBT had happened to observe 3I Atlas during the alignment window. The answer was no. But Ramirez was intrigued. We can point at it, she said during a phone call on September 28th. If you think there's a reason to. I don't think there's a reason, Fletcher replied carefully. But I can't rule it out. That's not exactly a strong scientific justification. I know. Ramirez sighed. Look, we've been through this before. Oumuamua. Everyone wanted us to point at it. We did. We spent hours looking for signals. We found nothing, and we got roasted for it. People said we were chasing UFOs. That we were wasting telescope time on science fiction. Why do you? I remember. So, unless you have something more than a geometric coincidence, I don't think we can justify it. Fletcher didn't push, because Ramirez was right. The alignment was suggestive, but it wasn't evidence. And evidence was the currency of science. Without it, you were just speculating. But the alignment bothered him. Not because he believed 3I Atlas was artificial, But because the geometry forced a question that was difficult to ignore, if an interstellar object were trying to communicate, how would we know? We'd been assuming that signals would be obvious. Bright, dark, persistent, narrowband radio emissions at a frequency that screamed artificial. The kind of thing SETI had been searching for since the 1960s. But what if the signal wasn't like that? What if it was subtle, transient, embedded in the object's dynamics rather than broadcast from a transmitter? Fletcher pulled up the light curve data again. The periodic brightness variations. The spin-up. The green ion tail misaligned with the solar wind. The deceleration. All of it could be natural. But all of it could also be deliberate. He hated the word deliberati. It implied intent. And intent implied intelligence. And an intelligence was the third rail of interstellar object research. Touch it, and your career could die. But the word wouldn't leave his mind. On September 29th, Dr. Raman Sikora published a blog post on his university's astronomy outreach page. The post was titled, Interstellar Object 3 Atlas and the Alignment Coincidence. Should we look harder? It was written carefully. Sikora emphasized the natural explanations. He acknowledged the low probability, but noted that low probability events happen all the time. He cited the mediocrity principle, the idea that Earth is not special, and therefore shouldn't expect to be singled out by cosmic visitors. But he also posed a question. If we had the opportunity to observe an interstellar object during a rare geometric alignment, and we chose not to because we were afraid of looking foolish, would we regret it later? The post got shared. A lot. Twitter, Reddit, astronomy forums. Within 2 days, it had been viewed over 100,000 times. Journalists started emailing. Science communicators started making videos. The discourse around 3E Atlas, which had been mostly confined to academic circles, suddenly went public. And with publicity came pressure. On October 1st, the Green Bank Telescope received an anonymous donation earmarked for high-priority transient follow-up observations. The amount was substantial, enough to fund several days of observing time. The donor's only request was that the telescope observe 3E Atlas during its remaining visibility window. Dr. Sofia Ramirez called Fletcher. "Okay," she said. "We'll do it. 4 hours. L-band and C-band. Full polarization. We'll look for narrow-band signals, broadband emissions, and anything anomalous." When? Fletcher asked. "October 3rd. That's the next available slot. The alignment will be over by then." "I know, but it's the best we can do." Fletcher thanked her and hung up. Then he sat in his office and stared at the orbital plot on his screen. The alignment had been real. Brief, but real. And they had missed it. Maybe there had been nothing to find. Maybe the coincidence was just that. A coincidence, meaningless and random. The kind of thing that happens when you roll the dice enough times. But maybe not. And the uncertainty, quiet and insistent, refused to go away. This is not science fiction. This is September 2025. Chapter 10, September 29th. What Cassini taught us too late. Sometimes the most important data is the data you almost threw away. On September 29th, 2025, Dr. Hannah Orr was giving a guest lecture at Caltech on the legacy of the Cassini mission. Cassini had orbited Saturn for 13 years, from 2004 to 2017, and had revolutionized our understanding of the ringed planet, its moons, and the complex dynamics of planetary systems. It had discovered geysers on Enceladus, lakes of liquid methane on Titan, and intricate structures in Saturn's rings that defied simple explanations. But the lecture wasn't about those discoveries. It was about what Cassini had missed. Orr pulled up an image on the screen, a grainy, low-resolution shot of Enceladus taken during one of Cassini's early flybys in 2005. The image showed the moon's southern hemisphere, pockmarked with fractures and bright streaks. At the time, scientists had noted the unusual surface features, but hadn't understood what they meant. It wasn't until 2015, 10 years later, that a team of researchers reanalyzed the data and realized that the bright streaks were plumes of water vapor erupting from subsurface oceans. The evidence had been there all along. In the temperature maps, in the spectroscopic data, in the gravitational measurements. But it hadn't been recognized because no one had been looking for it. We were looking for rings, Orr told her students. We were looking for moons. We were looking for what we expected to find. And because of that, we almost missed one of the most important discoveries in planetary science. Linton. One of the students raised a hand. Why didn't they see it earlier? Because, Orr said, the data didn't fit the models. The temperature anomalies were too localized. The spectral signatures were too faint. The gravitational variations were at the edge of the noise. Every individual piece of evidence could be explained away. It was only when someone put all the pieces together and asked a different question. Not, is this consistent with a dead moon? But what if this moon is active? That the answer became obvious. She paused. The lesson is this: anomalies don't announce themselves. They hide in the noise, waiting for someone to ask the right question. After the lecture, Orr sat in her office and thought about 3A Atlas. The object had anomalies. Lots of them. Deceleration, without visible gas. An ion tail pointing the wrong way. Thermal properties, inconsistent with the optical spectrum. A fractured, porous structure revealed only by light curve analysis. A geometric alignment with Earth and the Sun during a narrow observational window. Every single anomaly could be explained individually. Low-level outgassing. Magnetic field interactions. Subsurface, venting, distortion. Random geometry. Natural, plausible, mundane explanations. But what if they were asking the wrong question? What if the question wasn't, is this object natural? But what would an interstellar probe look like? Orr opened a new document on her laptop and started writing. She wasn't writing a paper. Not yet. Just notes. Thoughts. A thought experiment. If you wanted to send a probe to another star system, what would you build? First, you'd minimize mass. Every kilogram costs energy. You'd want the smallest, lightest object that could still survive interstellar transit. Probably elongated, to reduce cross-section and minimize impacts with interstellar dust. Probably porous, to reduce overall density and improve thermal insulation. Second, you'd need propulsion. But carrying fuel is expensive. So maybe you'd use solar radiation pressure. Or a solar sail. Or maybe you'd use the star itself, skim close during perihelion, gather energy. That would look like deceleration. It would look like non-gravitational dynamics. And it wouldn't require visible exhaust. Third, you'd need to survive the journey. Interstellar space is harsh. Cosmic rays. UV radiation. Micrometeorite impacts. You'd need shielding. A radiation-hardened crust. Maybe carbonaceous material, good for absorbing high-energy particles. That would look like a carbon-rich, volatile pore surface. It would look like a dead rock. Fourth, you'd need a way to communicate. But omnidirectional broadcasting is inefficient. So maybe you'd wait for a geometric alignment. Earth, Sun, probe. Minimize a path loss. Maximize signal strength. And maybe you'd use a subtle signal. Not radio. Something else. Something we might not recognize unless we were looking for it. Or stop typing. Because what she'd just written wasn't science. It was speculation. And speculation without evidence was just storytelling. But the description fit uncomfortably well. She pulled up the latest data summary from the 3 Atlas collaboration. Deceleration. Confirm. Ion tail. Confirmed. Thermal anomaly. Confirm. Fractured structure. Inferred. Alignment. Observed. Every piece of data was consistent with a natural object. But every piece of data was also consistent with something else. She thought about Cassini again. About the plumes of Enceladus, hiding in the data for 10 years. About the geysers that no one had predicted, because no one had thought to ask the question. What if 3I Atlas was hiding something too? not because it was trying to hide, but because we weren't asking the right questions? On September 30th, Orr sent an email to Dr. Jerome Fletcher at STSCIT. Jerome, I've been thinking about Cassini, about how long it took us to recognize the Enceladus plumes. I think we might be making the same mistake with 3I Atlas. We're trying to fit the data into existing models instead of asking what the data is trying to tell us. I'm not saying it's artificial. I'm saying we should stop assuming it's not. Non somen, and desintelligit. Fletcher replied 2 hours later. I agree. But how do we test it? That was the problem. How do you test for artificiality? You couldn't just point a telescope at an object and ask, are you a probe? You needed specific, falsifiable predictions. You needed experiments. You needed criteria. Orr drafted a list. Potential observables for artificial origin. Non-random surface geometry. Repeated patterns, angular features, specific symmetries. Active maneuvering, inconsistent with natural outgassing, trajectory changes without mass loss. Electromagnetic emissions at frequencies not explainable by thermal or plasma processes. Anomalous radar returns. Hollow interior, structured cavities. Isotopic ratios, inconsistent with stellar nucleosynthesis, engineered materials. Temporal correlations between dynamic behavior and geometric alignment, deliberate signaling. Most of those observations were beyond current capability. They'd need radar. They'd need high-resolution spectroscopy. They'd need close-up imaging. They'd need a spacecraft. And they didn't have any of that. They had ground-based telescopes, a few hours of Hubble time, and a rapidly closing observational window. But they had one chance left. The Green Bank Telescope observation on October 3rd. 4 hours. L-band and C-band. Looking for signals. It probably wouldn't find anything. Statistically, almost certainly wouldn't. But almost certainly wasn't the same as definitely. And in the space between those two words, possibility lived. On October 1st, Dr. Carla Mendez published an op-ed in Sky and Telescope magazine. The piece was titled The Cassini Lesson, Why We Should Look Harder at 3 Atlas. She didn't use the word artificial. She didn't speculate about probes or aliens. She just made a simple argument. Extraordinary claims require extraordinary evidence, but extraordinary observations require extraordinary attention. And 3I Atlas, whatever it was, deserved more than cursory observation and premature conclusions. The piece got attention. Not viral, but enough. Enough that a few more telescopes added 3I Atlas to their observing queues. Enough that a few more researchers started looking at the data with fresh eyes. Enough that, maybe, someone would ask the right question. Because sometimes the most important discoveries are the ones you almost miss. The ones hiding in the noise, waiting for someone to stop, look closer, and ask, what if? This is not science fiction. This is October 2025 2. Chapter 11. October 2nd. Thermal maps that don't cool down. Infrared astronomy is the art of measuring heat you cannot see. On October 2nd, 2025, Dr. Hannah Orr received the final process data from NASA's Infrared Telescope facility. RTF had observed 3I Atlas over 4 consecutive nights, September 28 through October 1st, using the MIRC instrument at multiple wavelengths between 8 and 13 micrometers. The goal was to construct a thermal map of the object's surface, tracking how temperature varied with rotation and solar illumination. Thermal mapping is straightforward in principle. As an object rotates, different parts of its surface face the sun. The illuminated side heats up. The shadowed side cools down. By measuring the infrared emission at different rotation phases, you can build a map showing temperature distribution across the surface. This tells you about the object's shape, composition, and thermal inertia, how quickly it responds to heating and cooling. For a bare rock in space, thermal inertia is low. It heats up fast and cools down fast. For an icy object, thermal inertia is higher. Ice stores heat and releases it slowly. For porous, insulating material, thermal inertia can be very high. Heat penetrates slowly, and once it's there, it stays. Or open the thermal map and frowned. The object was rotating with an 8.3-hour period, now well established from optical light curve analysis. The map showed brightness variations corresponding to different surface regions coming into view. All. But the temperature distribution was wrong. The illuminated side, the hemisphere facing the sun, was about 195 Kelvin, consistent with previous measurements. But the shadowed side, which should have been much cooler, was only 10 degrees colder. 185 Kelvin. That was barely a drop. Or on a thermal model. For a solid rock with typical thermal inertia, the day-night temperature difference should be at least 50 Kelvin. For a porous, insulating surface, maybe 30 Kelvin. But 10 Kelvin? That implied either extremely high thermal inertia or an internal heat source. She checked the data again. No errors. No calibration issues. The signal was clean. She called Dr. Mikhail Sokolov at JPL. "I need you to look at the thermal map," she said. Sokolov pulled up the file. He was quiet for a long time. "This doesn't make sense," he finally said. "I know. Either the surface is conducting heat incredibly efficiently, or something is generating heat internally. Comets don't generate internal heat." "No, they don't." Or ran a quick calculation. If the object were outgassing, sublimating subsurface ice and releasing latent heat, that could warm the interior. But you'd need a lot of outgassing. Kilograms per second .t. And that would produce a visible coma and measurable spectral emission. 3 Atlas showed neither. What about radioactive decay? Sokolov suggested. If the object is rich in long-lived isotopes, potassium-40, thorium, uranium, decay heat could keep the interior warm. For a kilometer-sized object, the heat production would be minuscule. Maybe a few watts. Not enough to explain this. Then what? Or stared at the map. The illuminated side. The shadowed side. Almost the same temperature. As if heat were being redistributed internally. As if the object had a thermal management system. She didn't say that out loud, but she thought it. By October 3rd, the anomaly had been confirmed independently by Dr. Raman Sikora, who obtained thermal data using the Large Binocular Telescope's infrared camera. Same result. Minimal day-night temperature, gradient, uniform thermal emission across the rotation phase. Sikora proposed a structural explanation. If the object is highly porous, 18% void fraction, like the light curve suggests, heat could be trapped in subsurface cavities. The voids act as insulation, preventing rapid cooling. Wouldn't say or tested the idea with a numerical model. She simulated a porous, fractured body with irregular cavities and calculated the thermal evolution over one rotation period. The model did show enhanced heat retention, but it still predicted a day-night difference of at least 20 Kelvin. Not 10. Maybe the rotation axis is oriented such that the entire object receives continuous illumination, Dr. Carla Mendez suggested during a video call. No true day-night cycle, just gradual variations. Or check the rotation axis derived from the light curve. It was tilted at 65 degrees relative to the ecliptic. That meant there was a day-night cycle. Not extreme, but present. Could there be subsurface ice conducting heat? Dr. Jerome Fletcher asked. Ice is a terrible conductor, Orr replied. It insulates. It doesn't conduct. What if it's not ice? What if it's metal? The suggestion hung in the air. Metals are excellent thermal conductors. A metallic core, or a network of metallic veins running through the object, could redistribute heat efficiently, equalizing temperature across the surface. But comets aren't metallic. Asteroids can be. M-type asteroids are largely iron-nickel, but they're also dense, typically 5 to 7 grams per cubic centimeter. 3I Atlas's estimated density, based on the light curve and assumed size, was closer to 1.5 grams per cubic centimeter. More like a comet or a carbonaceous asteroid. Not metal, unless the metal was internal. A dense core surrounded by a porous, carbonaceous shell. That would lower the average density while still allowing heat conduction. Or ran the numbers. If 3A Atlas had a metallic core comprising 10% of its volume, surrounded by a carbonaceous mantle, the thermal behavior could match the observations. The metal would conduct heat. The mantle would insulate. The surface temperature would be nearly uniform. But that raised a new question. How do you get a metallic core inside an interstellar comet? Planetary differentiation could do it. Heat a protoplanet enough, and the metal sinks to the center while the silicates and ices float to the surface. But differentiation requires significant heat, either from radioactive decay in a large body or from collisional energy during formation. A kilometer-sized object wouldn't generate enough heat to differentiate, unless it had been part of something larger. A fragment of a differentiated body, a piece of a shattered planet or moon. That was plausible. Collisions happen. Planets break apart. Fragments get ejected. Some travel through interstellar space for millions of years and eventually enter another star system. But a fragment that's small, with a metallic core intact, would be unusual. Most collision fragments are rubble, mixed compositions, not layered structures. On October 4th, Orr sent a message to the collaboration group. I think we're looking at a differentiated fragment, possibly a piece of an exoplanet or exomoon that was disrupted early in its history. The metallic core explains the thermal properties. The carbonaceous mantle explains the optical spectrum. The porosity explains the light curve. It's exotic, but it's consistent with all the data. Fletcher replied first. Differentiated fragments are rare. What are the odds that one happens to pass through the inner solar system during our observing window? Orr didn't have a good answer for that. The odds were low, but low probability events happen. And every interstellar object, by definition, is rare. Mendes replied second. If it's a fragment, where's the parent body? Can we trace the trajectory back? Sikora ran the calculation. He extrapolated 3I Atlas's orbit backward through space, accounting for gravitational interactions with the Sun and planets, and traced it into interstellar space. The trajectory pointed generally toward the constellation Lyra, but with significant uncertainty. Without knowing the object's velocity 10 million years ago, you couldn't pinpoint an origin. It could have come from anywhere within a 500 light-year radius, Sikora wrote. That's thousands of star systems. No way to narrow it down. So they had a plausible explanation, differentiated fragment, but no way to confirm it. The thermal map was consistent with a metallic core, but it was also consistent with other mechanisms they hadn't thought of yet. The data supported the hypothesis, but didn't prove it. And that, Orr realized, was the recurring theme of 3 Atlas. Every explanation fit some of the data. None fit all of it. And the object, silent and distant, refused to clarify. On the evening of October 4th, Orr stepped outside her office at Caltech and looked up at the sky. Somewhere out there, 60 million kilometers away, a small dark object was tumbling through space, carrying heat it shouldn't have, glowing faintly in infrared light that no human eye could see. It was strange. It was anomalous. It was, in every measurable way, unlike anything they'd cataloged before. But strange wasn't the same as impossible, and anomalous wasn't the same as artificial. Unless it was. This is not science fiction. This is October 2025, Chapter 12. October 5th. The cost of certainty. Dr. Jerome Fletcher had stopped sleeping well. It wasn't the data. The data was manageable. Confusing, yes. Contradictory, absolutely. But data was just data. You collected it, analyzed it, published it, and moved on. That was the job. What kept Fletcher awake was the gap between what they knew and what they could say. On October 5th, he sat in his office at the Space Telescope Science Institute and stared at the draft paper on his screen. Observational constraints on interstellar object 3I Atlas, non-gravitational dynamics, anomalous spectroscopy, and unresolved geometric structure. 16 pages, 3 tables, 8 figures, 47 citations. It was a good paper, careful and thorough, but it presented the observations objectively, outlined possible explanations, and concluded with a call for further study. It did everything a scientific paper was supposed to do, except say what he was actually thinking. What Fletcher was thinking, what he'd been thinking since mid-September, was that 3 Atlas didn't act like a comet. It didn't act like an asteroid. It acted like something that was designed to move through interstellar space without announcing itself. But you couldn't write that. Not in a peer-reviewed journal. Not unless you had ironclad evidence. And they didn't have evidence. They had anomalies. Suggestive, persistent, statistically improbable anomalies. But not proof. The problem was that absence of evidence worked both ways. If they published a paper saying this object is probably natural, and here are some plausible explanations, they'd be ignoring the fact that the explanations didn't actually fit the data very well. They'd be sweeping the anomalies under the rug. But if they published a paper saying this object's behavior cannot be explained by known natural processes, and we should consider alternative hypotheses, they'd be inviting a firestorm. The media would twist it. The public would sensationalize it. And the scientific community would quietly distance itself from them. Fletcher had seen it happen before. In 2018, after Oumuamua's acceleration was confirmed, Professor Avi Loeb at Harvard had published a paper suggesting the object might be artificial, specifically a light sail. The paper was careful. It acknowledged the low prior probability. It outlined natural alternatives. But it also made the case that, given the data, an artificial origin could not be ruled out. The response had been brutal. Other astronomers had written rebuttal papers, arguing that Loeb's hypothesis was unnecessary and unscientific. Journalists had written op-eds accusing him of attention-seeking. Online forums had mocked him as a crackpot. And while Loeb had weathered the storm, his reputation was strong enough to survive. The episode had sent a clear message to the rest of the community. Don't go there. Don't mention the A word. Don't even hint at it, unless you want to be ridiculed. Fletcher didn't want to be ridiculed, but he also didn't want to lie. On October 6th, he called Dr. Carla Mendez in Madrid. I don't know how to write this conclusion, he said. Write what we know, Mendez replied. The object decelerates. It has an ion tail. The thermal properties are anomalous. The structure is porous. We don't have a good natural explanation. That's all true. Just say that. And if reviewers ask why we're not considering alternative hypotheses, we are considering them. We just can't test them yet. That's evasive. It's accurate. Fletcher leaned back in his chair. Carla, what do you actually think this thing is? Mendez was silent for a long time. I think, she finally said, that it's probably a comet. A weird comet. A comet with unusual composition and dynamics that we don't fully understand yet. I think in 5 years, someone will figure out the right combination of volatiles and surface processes to explain everything, and we'll all look back on this and laugh at how complicated we made it. But I'm not certain, and I don't like not being certain. That was the core of it. Science was built on uncertainty, on questioning assumptions, testing hypotheses, revising models. But scientists, as humans, craved certainty. They wanted definitive answers. And when the data didn't provide them, the instinct was to force a conclusion. To pick the explanation that was least uncomfortable and commit to it. Natural was less uncomfortable than artificial. Random was less uncomfortable than deliberate. And so the community, consciously or not, biased itself toward those conclusions. Fletcher thought about that a lot. About bias. About the cost of being wrong. If they said 3 Atlas was natural and it turned out to be artificial, they'd have missed one of the most important discoveries in human history. But if they said it might be artificial and it turned out to be natural, they'd have wasted time, damaged their credibility, and fueled conspiracy theories for decades. Which mistake was worse? Dr. Hannah Orr at Caltech had a different perspective. I don't think we should be afraid of being wrong, she said during a 3-way call on October 7th. Being wrong is part of the process. What we should be afraid of is not asking the question. The question being, Fletcher asked, could this be artificial? Not is it, but could it be? And if the answer is, we don't know, We say that. We don't pretend we know. We don't force a conclusion just because it makes everyone comfortable. That's not how peer review works, Mendes said. Reviewers want answers. They want models. They want a mechanism. Then we give them a mechanism. We say, here are 3 natural explanations that partially fit the data. Here's one artificial explanation that also partially fits. We can't distinguish between them with current observations. More data is needed. End of paper. And when the media headlines say, scientists say interstellar object could be alien probe, what do? Or side. We write a follow-up clarifying that could be doesn't mean is. And we deal with the consequences. Because the alternative is staying silent, and silence is also a choice. Done. Fletcher appreciated the idealism, but he'd been in the field longer than Orr. He'd seen careers derailed by association with fringe ideas. He'd seen good scientists become pariahs because they asked uncomfortable questions. The problem, he said quietly, is that the cost of being right about something controversial is almost as high as the cost of being wrong. On October 8th, the 3 of them finalized the paper. They kept the conclusion neutral. They presented the data. They outlined multiple hypotheses: low-level outgassing, subsurface venting, thermal stress fracturing, differentiated fragment, and, buried in the third-to-last paragraph, atypical structural or compositional properties, not yet encompassed by existing models. It was code. Anyone reading carefully would understand. But it was subtle enough to pass peer review without triggering alarm. They submitted the paper to the Astrophysical Journal letters on October 9. The reviewers' comments came back on October 20th. 2 reviewers recommended acceptance with minor revisions. The 3rd reviewer recommended rejection, calling the paper speculative and insufficiently grounded in physical mechanisms. Fletcher, Mendes, and Orr revised the paper, added 2 more citations, and resubmitted it on October 24th. It was accepted on November 3rd, scheduled for publication in the December issue. By then, 3I Atlas would be invisible, deep in solar conjunction, gone. But the questions would remain. The anomalies would remain. And somewhere quietly, other researchers would read the paper and wonder, what if? Because certainty has a cost, and sometimes the cost of certainty is the truth. This is not science fiction. This is October 2025, Chapter 13. October 8th, the last clean data. October 8th, 2025, was the last day of pristine observation. Dr. Elena Vasquez knew it as soon as she saw the trajectory projections. 3 Atlas was at 1.220 from the Sun now, about 182 million kilometers, and still approaching perihelion. Solar radiation was intensifying. The object's surface temperature had risen from 190 Kelvin to 215 Kelvin over the past 2 weeks. And while that was still far below the threshold for vigorous ice sublimation, it was warm enough to start altering surface chemistry. Any volatiles that had survived millions of years of interstellar transit, shielded by a carbonaceous crust, locked in subsurface ice, or trapped in mineral matrices, would now begin to mobilize. Carbon chains would fragment. Frozen gases would soften. Organic compounds would polymerize or decompose. The object was changing. Slowly, irreversibly, the pristine interstellar state was degrading into something else. By October 15th, it would be too late. The chemistry would be contaminated. The signatures erased. What they had now was all they would ever have. Vasquez sent a message to the collaboration group. This is it. Last call. If there's any observation we didn't do, any instrument we didn't use, this is the time. The responses came quickly. Dr. Carla Mendez in Madrid. Velti is finishing final spectroscopy tonight. I pushed for 1 more night. They gave me 4 hours. That's all. Dr. Jerome Fletcher at STCI. Hubble is done. No more director's time available. What we have is what we have. Dr. Hannah Orr at Caltech. RTF is still observing. I'm getting thermal maps through October 10th. After that, the object's too close to the sun in the sky. Solar exclusion zone. Dr. Ramon Sikora at Arizona. LeBT has one more night scheduled. October 9. Weather permitting. Jinsis. Dr. Mikhail Sokolov at JPL. Flala has time on October 10th. Final radio sweep. I'm not optimistic, but we'll try. And that was it. The infrastructure. The machinery of observation. Grinding forward, limited by budgets and scheduling, and the simple fact that telescopes could only point in one direction at a time. On October 8th, the Green Bank telescope completed its 4-hour observation. Dr. Sofia Ramirez processed the data overnight and sent the results to Fletcher on the morning of October 9th. No detections. Fletcher opened the report. GBT had observed at L-band 1, 2 GHz, and C-band 4, 8 GHz, with full polarization, searching for narrowband signals, broadband emissions, pulsed signals, and any anomalous radio features. The sensitivity was excellent, good enough to detect a 1 kilowatt transmitter at 3 atlases distance. Nothing. No signals. No emissions. Radio silence. The report concluded, no evidence for artificial radio transmission. Upper limits consistent with passive thermal emission from a 1 kilometer body at 215 Ka. Fletcher forwarded it to the group. No one replied, because there was nothing to say. The null result was expected. It was the most likely outcome, and yet, irrationally, there had been hope. Now there wasn't. On October 9th, the Large Binocular Telescope observed 3I Atlas for the final time. The weather was clear. The seeing was good. Sikora captured high-resolution images in 5 filters, covering ultraviolet to near-infrared, and obtained a deep narrowband exposure centered on the CEO of force emission line at 557.7 nanometers. The ion tail was still there, fainter now, but present, still misaligned, still pointing 11 degrees away from the expected solar wind direction. Sikora measured the tail's brightness and calculated the ion production rate. It was low, about 1023 ions per second. For comparison, a typical comet near 1O produces 1026 to 1028 ions per second. 3I Atlas was 3 to 5 orders of magnitude weaker. Barely active, barely alive, but it was still outgassing something. Still emitting, still glowing faintly in forbidden oxygen. Sikora sent the image to Vasquez with a note. Last light curve point. Period is now 8.27 hours. Still spinning up. Vasquez added it to the master light curve and ran the fit again. The spin-up was real. Over 5 weeks, the rotation period had decreased by 0.04 hours. That implied a net torque, acting on the object, consistent with asymmetric outgassing, even though the outgassing was invisible. She stared at the curve for a long time. The slow, steady acceleration in rotation. The gradual loss of angular momentum or gain, depending on how the jets were oriented. The object was changing, responding to the sun, waking up maybe from a long cold sleep, or winding down. On October 10th, the Very Large Telescope obtained the final spectrum. Dr. Mendez had fought for one last night, and the scheduler had relented. 4 hours on X-shooter. Maximum integration time, pushing the signal-to-noise ratio as high as possible. The spectrum arrived on October 11th. Mendez opened it immediately. The continuum was the same. Flat, red-sloped, unremarkable. But there were new features. Faint emission lines that hadn't been present in the earlier spectra. She zoomed in. At 630 nanometers, a weak emission line. Forbidden? Toden. Consistent with the ion tail. At 656 nanometers, hydrogen alpha. Also faint. Also nu. Tau. And at 589 nanometers, something else. Broad. Diffuse. Maybe sodium. Maybe not. Mendez ran the wavelengths through a molecular database. The hydrogen alpha was easy. Ionized hydrogen, common in cometary comae, and ion tails. The sodium, if it was sodium, was unusual but not unprecedented. Some comets showed sodium emission when volatiles released from subsurface salts. But the combination, oxygen, hydrogen, sodium, suggested active chemistry. The surface was starting to sublimate. Slowly, weakly, but measurably. The clock had run out. Mendes wrote in her observation log. Final spectrum shows onset of sublimation activity. Pristine state no longer preserved. Further observations will measure solar-altered chemistry, not interstellar composition. She sent the spectrum to the group. Dr. Sokolov replied first. So we got it. Just in time. Vasquez replied second. Did we? Or did we miss the most important part? No one answered that. Because the question wasn't really about the data. It was about what the data meant. They had observed 3I Atlas for 5 weeks. They had obtained spectra, photometry, thermal maps, light curves, radio observations. They had measured its size, shape, rotation, temperature, composition, and dynamics. They had documented dozens of anomalies and published a paper outlining all of them. But they still didn't understand it. On October 12th, 3I Atlas crossed into the solar exclusion zone for most ground-based telescopes. The object was now less than 30 degrees from the sun in the sky, and observing it required pointing telescopes dangerously close to the solar disk. Most facilities prohibit such observations to avoid accidental damage to instruments. A few space-based observatories, Stereo, SOHO, the Solar Dynamics Observatory, could still see it, silhouetted faintly against the solar corona. But those instruments weren't designed for spectroscopy or high-resolution imaging. They were solar monitors. All they could do was track the object's position, which they did, day by day. 3I Atlas continued its slow fall toward the sun, decelerating slightly, spinning slightly faster, glowing faintly in oxygen and hydrogen. On October 15th, Dr. Fletcher compiled the final observational summary. He listed every instrument, every observation, every data point. 63 nights of telescope time, 17 different facilities, over 200 individual exposures, thousands of person-hours of work. And at the end of the summary, he wrote, "The pristine interstellar state of 3I Atlas has been lost. What we have observed is a snapshot, incomplete but irreplaceable, of an object in transition. The chemistry is now changing. The surface is now active. Future observations will tell us how this object responds to the sun. But they will not tell us what it was before it arrived." He saved the file and closed his laptop. Somewhere out there, 150 million kilometers away, a small, dark object continued its journey. Silent, inscrutable, carrying secrets that no telescope could quite resolve. The last clean data had been collected. The window had closed, and the questions remained. This is not science fiction. This is October 2025 Dardes. Chapter 14, October 12th, From Darkness to Light. On October 12, 2025, Elena Vasquez stood on the observation deck at the Atlas facility in Hawaii and watched the sun set over the Pacific. It was a clear evening. No clouds, no haze, just the smooth gradient of twilight fading from orange to purple to black. Somewhere out there, invisible to her eyes, 3I Atlas was still moving, still falling toward the sun, still changing. She thought about the object's journey, not the recent journey, the 5 weeks humanity had watched it, but the journey before. The millions of years drifting through interstellar space, the cold, the silence, the radiation slowly eroding its surface, carbonizing volatiles, fracturing ice, carving voids. Where had it come from? They didn't know. The trajectory pointed vaguely toward Lyra, but vaguely meant a sphere 500 light-years across. Thousands of stars, hundreds of planetary systems. No way to narrow it further. Had it formed around another star? Had it been ejected during planetary migration, the way Neptune's gravity had scattered countless comets into the Oort cloud? Or had it been part of something larger? A planet, a moon, that had been shattered by collision or tidal forces? Or had it been built? Vasquez didn't like that question. It was uncomfortable, unprovable, the kind of question that invited ridicule and conspiracy theories. But the data wouldn't let it go. The deceleration, the ion tail misalignment, the thermal uniformity, the fractured geometry, the geometric alignment, the spin-up without visible gas. None of it was impossible to explain naturally, but all of it, taken together, resisted easy explanation. It was like a puzzle, where every piece fit poorly. You could force them together. You could trim the edges and ignore the gaps. But the picture never quite resolved. She thought about Dr. Jerome Fletcher's question from 2 weeks ago. What would an interstellar probe look like? It would be small, mass efficient, elongated to minimize cross-section, porous to reduce density, covered in a radiation-resistant crust. It would use solar gravity for trajectory adjustments, venting small amounts of gas, or adjusting reflective surfaces to create thrust. It wouldn't broadcast loudly. It would wait for geometric alignments, minimize power, stay quiet. It would look, in other words, like an anomalous comet. But that didn't mean it was one, because evolution doesn't optimize for stealth. Nature doesn't care about cross-sections, or thermal management, or geometric alignments. Nature is messy, random, inefficient. And yet, occasionally, randomness produces order. Occasionally, natural processes create structures that look designed. Snowflakes, crystals, the hexagonal columns of basalt at the Giant's Causeway, all natural, all looking to the untrained eye like someone built them. Maybe 3I Atlas was like that. A natural object whose formation and history happened to produce features that look deliberate. Low probability, but not zero. On October 14th, Vasquez received an email from a graduate student at METI. The subject line was, "Question about 3 Atlas thermal data." The student had read the paper. She'd noticed the uniform thermal emission and run her own models. She wanted to know if the team had considered piezoelectric heating, thermoelectric effects and crystalline materials that could generate heat from stress or deformation. Vasquez hadn't considered it. She forwarded the email to Dr. Hannah Orr. Orr replied 2 hours later. "Interesting idea. But piezoelectric heating requires active deformation. Unless the object is fracturing in real time, it wouldn't produce sustained heat." The student replied again. "What if it is fracturing? What if the spin-up is causing internal stress? Slow breakup." It was plausible. Barely. If 3I Atlas was on the edge of structural failure, held together by tensile strength rather than gravity, the rotation could be slowly pulling it apart. Internal fractures would release energy. That energy would appear as heat. Or run a model. The energy release from fracturing was too small to explain the observed thermal uniformity. You'd need continuous, widespread fracturing across the entire object. That wasn't impossible, but it was, once again, a very specific scenario engineered to fit the data. "We're doing it again," Vasquez said during a call with Orr. "Finding explanations that technically work, but aren't really satisfying. Because the satisfying explanation is off limits," Orr replied. "The satisfying explanation is also unstable. For now," Vasquez sighed. "So what do we do? Just sit on this forever? Keep adding footnotes to papers saying, 'We can't rule out alternative hypotheses,' while never naming the hypothesis? What else can we do?" That was the question. What else could they do? They'd published the data. They'd outlined the anomalies. They'd called for further observation. And the community had responded with interest. Mild interest. A few follow-up proposals. A few conference presentations. But no urgency. No paradigm shift. No revolution. Because revolutions require proof. And they didn't have proof. They had a strange object that didn't quite fit existing models. That wasn't enough. It never was. On October 16th, Dr. Carla Mendez published a blog post. It was titled "What 3 of Atlas Taught Us About the Limits of Observation." The post was reflective, not technical. Mendez wrote about the challenges of studying interstellar objects, about the fragmentation of observational resources, about the difficulty of securing telescope time for targets that don't fit predefined categories, about the frustration of watching an object slip away before you've answered the most important questions. And she wrote about uncertainty. Science is built on the idea that we can know things, that we can observe, measure, test, and eventually understand. But sometimes, the universe gives us a glimpse of something we're not quite ready to understand. Not because we lack the tools, but because we lack the framework. 3 Atlas is one of those objects. We observed it as well as we could. We documented its behavior. We proposed explanations. But in the end, we don't know what it was. We only know what it wasn't. And maybe that's the real lesson. That certainty is rarer than we think. The post got shared widely. Thousands of people read it. Dozens commented. Most agreed. Some accused Mendes of hedging, of refusing to commit to a conclusion. A few accused her of hinting at aliens without saying it outright. Mendes didn't respond to the comments because there was nothing to say. She'd written what she believed. That was enough. On October 18th, 3 Atlas reached perihelion. It passed 0.970 from the Sun, about 145 million kilometers, still on its hyperbolic trajectory, still bound for interstellar space. Its velocity at perihelion was 38.4 kilometers per second relative to the Sun. Fast enough to escape, fast enough to leave forever. The Solar and Heliospheric Observatory, orbiting at the lone Lagrange point, captured a low-resolution image. A faint dot against the Sun's corona, moving, silent, and then it was gone, swallowed by the Sun's glare. Observations would resume in December, when the object emerged on the far side of the Sun. But by then, it would be faint, distant, altered by solar heating. The pristine interstellar chemistry would be gone. The anomalies would be harder to detect. And the community would have moved on to other targets, other mysteries, other questions. On October 20th, Dr. Jerome Fletcher wrote the final entry in the 3i Atlas observation log. We watched an interstellar object pass through our solar system. We documented its properties. We measured its dynamics. We noted its anomalies. In the end, we were left with more questions than answers. That is not a failure. That is science. The universe does not owe us explanations. It only offers data. And sometimes, the data is enough to show us how much we don't yet understand. He closed the file and archived it. Somewhere out there, beyond Mars, beyond the asteroid belt, beyond the reach of human telescopes, a small object continued its journey. From darkness to light, and back to darkness again. It had arrived, unannounced. It had behaved strangely. And it had left without explanation. Humanity had watched. Humanity had measured. Humanity had wondered. And the object, indifferent to all of it, moved on. Because that is what travelers do. They pass through. They leave traces. And they continue. This is not science fiction. This is October 2025. This is what it means to watch the universe, and realize that sometimes the universe watches back.